Welcome back, and we're ready for our second talk, which will be given by Professor Christina Sormani, who's a faculty here at the Graduate Center and at Lehman College. And she will talk about limits of manifolds with positive scalar curvature, and this is joint work with Yusuf and Jorge Basilio.
Thank you very much for the opportunity to speak. I'm going to say well, maybe I'll say it at the beginning. Okay. So I did write down something to say to Joseph. I wrote it down because it's hard to say these things. Okay. Okay. All right. So I just wanted to say that when I first came to CUNY in '99, I had a new baby and I had 2 more before tenure. And during that time, my chairman at Lehman was very difficult and the teaching load was very high. And I took as long unpaid maternity leaves as possible. And Joseph welcomed me here. He gave me an office here. I spent most of my time here. And that was a big difference in my career because I spent time in a location where I was welcome. Edgar Feldman and Isaac Chevelle were here. We had this really nice differential geometry seminar where everyone was polite to each other and respectful towards the speakers. And it was a contrast. And it was really nice. And I worked hard and I got an appointment here and I'm proud that I did that. And tenured and full professor and all that since, and the kids are in college and high school. Okay, but that's a long time ago, but it really did make a huge difference in my life. There were times I seriously thought about quitting academia. I never considered quitting mathematics. Almost all the women who went to Courant with me had left academia for industry. I mean, industry, they worked for Intel, they worked for Google, they worked for all these amazing corporations. They were respected there because if you get a result, the company wants the result, okay? And so I was tempted away because, these people call me and say, hey, we'd like you to come, but Joseph is one of the reasons I stayed at CUNY. And so I just really wanted to thank you. You make a very positive environment here. And, okay? And on behalf of Jorge, I want to thank you and all the other doctoral students. He is totally committed to them, and he really bails them out in times of trouble. And there have been times where students work hard, but then they have a difficulty, and some life events happen, and they lose track of things. And Joseph really always kept track of them and helped bring them back in. So that's another really important thing that Joseph's always done for our department. He really cares about the students. Everyone, including us geometers. And so I just want to thank you for that too. All right. So today's talk is about a joint paper with Joseph and Jorge, and it's the beginning of Jorge's thesis. And then there's more parts later. So I just want to focus on the part that Joseph worked with us on. So let me give some background on why we did this project. So when you're considering limits of manifolds, limits of Riemannian manifolds, and I'll just stick to compact ones. So I'll call them MJ, and they'll all have the same dimension, and they'll all be compact. I never can decide if I just should go before or after, so I just put them on top. Okay, so limits of compact Riemannian manifolds, and so what you usually have is some condition. So if the MJs have sectional greater than or equal to 0, then the appropriate notion of convergence one should use is that Gromov-Hausdorff convergence. So you have MJ Gromov-Hausdorff to some m infinity. This is a subsequence. This is actually compactness. So this is Gromov-Hausdorff. And m infinity is an Alexandrov space with non-negative curvature. Alexandrov curvature greater than equal to 0. All right, so that's basically saying that if you have triangles behaving right, so you compare triangles, so here's your M, you have your triangle here, sectional curvature means that it bows out a little more than it does in Euclidean space with the same side lengths. So if these three side lengths match, the comparison theorem says that this length, and I'll go the same distance t here, the Euclidean length LE and LM is bigger or equal to the LE. That property is conserved under Gromov-Hausdorff convergence because Gromov-Hausdorff convergence is defined in terms of lengths and distances between things. All right, so that's with sectional greater than 0. The next step is to consider Ricci greater than 0. Then your MJs Gromov-Hausdorff converge with a measured Gromov-Hausdorff convergence to an M infinity. So now this guy was only a metric space, an X and a D. This is a metric space. But M infinity is a metric measure space, so it has a measure on it. And Cheeger-Colding, I should say all of this is Gromov. Cheeger-Colding showed that this limit M infinity has non-negative Ricci in a generalized sense. So let me explain the generalized non-negative Ricci. If you have a large ball, radius big R, and a smaller ball, or radius little r, this is an Euclidean space of the same dimension, and you compare it to I gotta curve it a little bit. This is the M. Okay? You compare it to the same pair of ratios here. And Ricci non-negative says that the volume of the ball, the smaller ball, is bigger than you expect. Omega n r to the n. Omega n r to the n. This is Bishop Gromov. So that's the property.
Christina, is that equivalent to being, Ricci being bigger than 0? Or is it?
Shio has basically proven that for if it's every P and R. And then, but that's much, much more recent. Cheeger-Colding showed that the M infinities have the same ratios. So M infinity mu, the mu has the same thing. So you get mu of a ball over mu of a big ball, bigger or equal to R. And then, since then, there was Lott, Villani, and Sturm. Sturm really clarified the measured convergence. This measured convergence here was originally introduced by Fukaya. Sturm has a better sort of definition for it called the D distance, which is not quite the same as the Fukaya one, and it works even if you don't have Gromov-Hausdorff limits. But anyway, they studied more properties of M infinity is what's called a CD and O space, or ON. I'm dyslexic, so one is the dimension, one is the curvature. And since then, there was Ambrosio Ziegler Savare, who defined RCD spaces, which means it's locally infinitesimally actually like Euclidean. So it's not Finn's law, which is a big deal. So these kinds of spaces were the generalized classes of spaces. So we have the generalized class of non-negative sectional, is these Alexandrov spaces. We have the generalized classes of non-negative Ricci. You could do CDON, which is not quite as strong as the RCDON spaces, but these are both two kinds of generalizations. All right, so all of these spaces are, there's just a little more work in the red zone, so let me just put a little more up here. I don't want to leave this out. Virago, Gromov, and Perelman. Virago, Gromov, Perelman in the 90s proved that these spaces are actually rectifiable. So they're covered with countably many bilogic charts. Covered almost everywhere by countably many bilogic charts. And Cheeger can get at least that much and more about the M infinity, okay? So you have this background, and then, as you can see, Gromov is fundamentally involved in both this question and this one, since he did the Bishop-Gromov comparison theorem and the Gromov-Hausdorff definition. So then Gromov has a question. What is the natural convergence notion of convergence if the MJs have scale greater than 0 and what are the limit spaces? Now, scalar is a little bit more problematic because it doesn't have a nice, we could call these quasi-local or semi-global properties like these. I mean, there's properties about the whole integral of scalar over the whole thing. There's properties about scalar infinitesimally, but we don't have really very nice comparison theorems like these that work on scale R. That's fixed for the whole sequence. So, I mean, for example, one of the properties you have for scalar, I just always have to look this one up because it's got a constant, is that it's an infinitesimal property. So, for example, the scalar curvature at a point of a Riemannian manifold is the limit as R goes to 0 of 30. Volume in Euclidean space. Volume in Euclidean space of a ball. I'll say it's 0R, doesn't matter. Minus volume in the manifold over volume in Euclidean space. Scalar curvature is the trace of the Ricci. Ricci is the trace of the sectional. The fact this comes out to be 30 is kind of weird, but okay. All right, so but this is an infinitesimal thing. You need to take a limit. And as you know with functions, right, if you have a property like that, you don't really expect it to carry over to the limit space. So there's been sort of a track, but you would like to have a notion of the limit space. You would kind of think the limit space ought to have this property. You'd have to have some more global property on the way, and then afterwards you would like to have this property. So actually Gromov suggested intrinsic flat convergence. It's a weaker notion of convergence. And the reason is there's two examples of importance might work. So let me just tell you a little bit why he thought that might work, okay? So, intrinsic flat convergence. Okay, first of all, this is designed almost explicitly to deal with questions involving scalar curvature. It's designed to deal with Ilmanin's example. So I'll draw Ilmanin's example because it's beautiful. Gromov isn't the only person who was worried about sequences of manifolds with non-negative scalar. So Ilmanin had brought this up actually at talk at Columbia, right, maybe 15 years ago or so. and he drew the following pictures. These are three-dimensional manifolds, and they're all diffeomorphic to S3, but what they have is the gravity wells on them. So there's the first one, say. And the second one, now you have more of them. That's too wide. Okay, so you get increasingly many gravity wells. This can be done, they're called gravity wells because you can think of these scalar non-negative naturally fits with a space-like manifold inside space-time, and there's some time symmetric conditions and things like that that imply scalar non-negative or positive energy condition, these sort of things. So they naturally, if you think in terms of gravity and general relativity, which is how Illman was thinking when he came up with the sequences, he was thinking, what if there were universes and they had lots and lots of planets? Which kind of is what universes have, right? Mm-hmm. So each of these is a planet that's equally, these planets are all equally deep wells. They've made a certain amount of depth because they bend space-time, they bend space. So each one of them is equally deep, but they're narrow and narrow, which actually means they have less mass, but they're getting more dense to make up for that. So you can actually, there might be a black hole in this room. Mm-hmm. You wouldn't know if it's a small enough one. So these are not black holes, they're actually just gravity wells because they're not broken. But they're getting deeper, they're equally deep, and this sequence has no Gromov-Hausdorff limit. For any subsequence. But of course, all of you know where it ought to converge, right? It ought to converge to a sphere. That's where you'd like it to converge. So Illman had asked this question, how can we get this to converge to a sphere? It looks kind of like LP or something, right? Something like that. So, the intrinsic flat convergence is designed to imitate flat convergence by Federer and Fleming, which also had to deal with problems of increasingly many wells. So there was flat convergence, which had a flat symbol on it by Whitney, Federer, and Fleming, which is back to the 1950s. And they were dealing with Plateau's problem and trying to find the smallest disk whose area that bounds this. They're looking for, find an embedding of D2 into E3 such that if you push forward the boundary of D2, you actually get the standard S1 sitting inside E3. That's a push forward symbol. So you've got these S1s sitting in E3, and you're looking for this, and what you do is you say, oh, okay, we'll look for a sequence of smallest area. And so they were looking for sequences of smaller and smaller area and take a limit, right? Take a sequence by J's, D2 of decreasing area. And this problem happened. You could have John Morgan has a beautiful picture of just how horrible these things can be. You can get them space filling in the limit. But you want the limit to just be, the flat disk, right? So they defined a flat convergence to do this. And so the way this actually converges in the flat sense, flat, sharp, flat. That's what they use. So we use an F for Federer Fleming. Okay. And that notion of convergence works because it's measuring not the distances or locations of anything, but rather the volume between the sequence and the limit. So basically, the flat distance between two things, say, phi 1, A1, I'll use the push forward notation, phi 2, A2, actually maybe these S's, is equal to the smallest, it's called mass. It's really volume, such that A plus boundary B is phi1 over S1 minus phi2 over S2. I'll just draw the picture and see what's going on. Sorry for this mess.
Christina, the recording doesn't go to that side.
Okay, is this board cylinder?
That's fine.
Okay, great. Thank you. Okay. So if this is phi1 number S1, and notice this is an oriented notion, and this is phi2 number S2, right? If you got those two guys there, then you measure the area between them. We're going to close it up with a little bit of an A. And that's the A. This thing is a mass, so it's a length or an area or a volume, and it's weighted in case there's overlapping. And the B is something one dimension higher, which fills in. That's the B. So it's basically measuring a filling, and it measures the filling volume between the two. M plus one dimensional volume. Okay, M plus one volume between two submanifolds. In a large Euclidean space. That's the Federer-Fleming version. If you want to learn more about this, you can read a 400-page geometric measure theory. Or you can read Frank Morgan's really nice short book, which is a guide to that and has actual precise references to those theorems, but has pictures. So he's like the picture guide to this world. All right, so that's
Federer-Fleming, and that's the beginning of Federer's geometric measure theory. And there's a whole world here I'm hiding. Okay, and then there's how can we use this to deal with these spaces, which is we're talking about sequences of manifolds, not submanifolds, and this whole old story was for submanifolds. So now you want to deal with manifolds, which is why we call it intrinsic. But you want the same kind of properties. So the best way to make something that makes Ullmann's example converge is to indeed use this notion. So what we do is, this is joint with Stefan Minger. He was a postdoc at NYU and was a little terrified to talk to Gromov, so he started hanging out at CUNY all the time. Okay, he was supposed to be Gromov's postdoc. Anyway, also Gromov was only there half the time. So we made up the intrinsic flat convergence, which is built completely on this flat convergence, but what you say is the intrinsic flat, we use the fancy F, between two Riemannian manifolds is, and we're imitating Gromov's definition of intrinsic Hausdorff. So Gromov called his Gromov-Hausdorff distance, he called it intrinsic Hausdorff because it's made with the exact same definition, but instead of using flat, he used Hausdorff distance. So here we say it's the infimum of the flat distance inside any metric space Z of the images. So now we've made them into manifolds. Okay, so we push them into the Z space. We measure their flat distance in Z, and we're infimuming over all mi's and all complete Z. This is a distance-preserving map. So distances between points in MI are exactly the same in their images in Z. Okay, this is exactly like Gromov's intrinsic Hausdorff distance. Gromov's Hausdorff distance is an infimum over all compact Z's, over all distance-preserving maps of the Hausdorff distance between these two guys in a metric space Z. Okay. So this seems like a reasonable notion. The thing that we need, though, is some difference between flat and Hausdorff, is that this is an oriented notion. So we definitely need these guys to be oriented. They actually have different values if you give them the opposite orientation. So it's not just orientable, oriented. We've given them an orientation. Okay, so now we have this notion, and what do we have from this is that the Illmann example converges. Okay, and that's the first reason why Gromov thought this might be the right one. All right. Now there's one catch here. I'm hiding it a little bit. You notice that this is a Z, and this is Euclidean space here. So I just snuck something up on you guys. So all of this Federer Fleming was extended by Ambrosio and Kirchheim in 2000. So Z complete. They extend all of geometric measure theory effectively in this amazing paper, including all of Federer Fleming's compactness theorems, and everything about integral currents and everything of that sort has been extended to metric spaces. And this is like one of the most important papers of the century. It's been cited. It's useful in so many different directions. All right, so we use that in order to do this, and Stefan was an expert on that work. He was an Ernst Lang student, and he had done work on their research before. So now we got this intrinsic flat convergence. The Illmann example converges, and then there's a really beautiful compactness theorem that's Stefan proved. So I call it the Wenger compactness theorem. And it says that if the MJs, I'll just say the volume of the MJs is less than or equal to V naught, and the diameter of the MJs is less than or equal to D naught, then the subsequence converges. Intrinsic flat converges to some M infinity. Okay? So that's very little conditions needed. No curvature bound needed at all to have a limit. But there's warnings. So let me give you some warnings. First of all, why do we have volume and diameter bounds? This basically is imitating the Federer-Fleming's compactness theorem. That's it, if you have a sequence of these guys and they have all located in a compact set of Euclidean space and they have uniform upper bound on their areas, then the subsequence converges. It was that's the Federer-Fleming compactness theorem. Ambrosio Kirchheim extended that theorem. If it has boundary, you need to also assume a uniform upper bound on the boundary. Okay, but what do the limit spaces look like? So the limit spaces for both Federer Fleming and Ambrosio Kirchheim, the limit spaces are, maybe I can erase this middle board here. The limit spaces of those guys are integral currents, which is the key thing. Let me just write it here. Limits are integral currents. So that means they're rectifiable. And I told you what rectifiable was. Rectifiable means that there are countably many by Lipschitz charts. Integral currents have one more nice thing about them, which is that the boundary also has countably many by Lipschitz charts, which isn't necessarily guaranteed just because you have countably many by Lipschitz charts. So the integral currents are rectifiable, and the limit spaces here, in this work, intrinsic flat convergence, the limit spaces are integral current spaces. We define that. Which is that they are a metric space with an integral current on them, and that the set of positive density of the current is actually equal to the metric space itself. So it's sort of saying that so in particular, the metric space itself has a countable collection of bi-Lipschitz charts. It has a boundary that also does. All right, and the boundaries, if the sequence of spaces converges, then the boundaries converges, things like this. All right, so this is what these M infinities are. They're these kinds of spaces. But there's one more problem. if you take a sequence like this is a nice sequence, the boundary's kept from collapsing. There is something called, there's two bad things that can happen, and they also can happen in the Federer-Fleming setting. We can have collapse, which is what happens when the volumes of the MJs go to 0. If the volumes of the manifolds themselves are going to 0, then they fill in with something going to 0 themselves. They can be the A's. They can be their own A's, and the B can be nothing. So if that implies that the MJs intrinsic flat converge to the 0 space. So there is this 0 space, which is one of these guys. It's empty set 0, 0. Okay, that happens. Okay, that's annoying. And there's something called cancellation. Both of these things are problems here as well that has to be dealt with whenever you apply this to do any of your geometric measure theory. And one way they stop it is by holding the boundary somewhere. It can't disappear if there's a boundary still at the end. You know, things like that. Okay, so cancellation is this picture, which happens in the Federer-Fleming example easily. If you have a sequence like this converges to something like this. That thin region can be filled in. It's very close to this guy. So this is called cancellation because opposite orientations coming together. All right, so this cancellation problem means entire things disappear, but it could also completely cancel. You could have something like this, and then the limit is nothing. 0 space again. Okay? That can also occur with Riemannian manifolds. And so these are problems. These are difficulties that you work to avoid. And then there's a neat thing, which is the doubling, which is nice, I think. Doubling is the fact that this keeps track of orientation so nicely. It notices if you have a sequence like this converges to something. Orientations here. It's over here, it's doubled. It's 1, 1, 1. So it keeps track of that it's going over a region twice. And that allows for the boundary to be well defined. So the boundary, in this case, for this sequence, right, this is the minus end of the boundary and the plus end, if it's one-dimensional, right? And this is the minus end and the plus end. And you really see that because of the 2. You realize that this is actually going around twice, so that's not part of the boundary happening there. Okay? So that's a nice effect. That's positive, but of course the counterpoint is you have canceling, which is the minus cancel. And then, of course, you can do the integer mod 2 version of everything, and then this would also disappear if you want. So people have done that. All right, so we have these 3 issues, and so then you say, okay, well, the good news is, for the Illman example, we had collapse, but of exactly what we wanted to collapse, which was all those thin little wells. So, back to non-negative scalar curvature. Have that element an example. And this intrinsic flat converges to an ordinary sphere because those things have small volume inside them. So basically, we can fill in all this volume. Okay, so the filling volume between MJ and the sphere. S3. So in our paper, we actually explicitly, constructed the filling. All right, so this was a positive situation because this is a problem with scalar curvature. There was no Gromov-Hausdorff limits because there could be increasingly many wells, but we have a way that cuts off the wells Now there's a limit, so everything's good. So then the question becomes naturally, okay, so now in what sense does the limit space have non-negative scalar? Because we have a limit space with this very little conditions. Volume, diameter, add scalar non-negative. You'll have a subsequence that converges. In what sense does M infinity have non-negative scalar? So Gromov made a vague conjecture, deliberately vague. So this is basically in his dozen problems, but he stated it more about a few years ago in other papers. So basically the statement is that if the MJs have volume less than or equal to V naught, diameter less than or equal to D naught, scalar equal to 0, does a subsequence converge to M infinity with scalar greater than 0.
Scalar infinity. No scalar. J.
Yes, thank you. Thanks. Whatever that means. That's generalized, right? I should just quickly remark. Remember at the beginning I said about the Gromov-Hausdorff limits? In the setting with sectional greater to 0 and Topanagov, or Topanagov curvature, or Alexandrov curvature greater than 0, or the Topanagov triangle comparison holding. In that setting, you will always get, if you put that curvature bound here, the subsequence does converge with the same curvature bound in intrinsic flat sense. Raquel Perales proved that, did the Alexandrov greater to 0. The Gromov-Hausdorff and intrinsic flat convergences agree. Okay, so then you get this kind of result. And for the Ricci case, Portuguese Portuguese and Medvedev, getting this backwards. Okay, Medvedev, Portuguese. And improved upon an earlier paper of mine with Wenger that says Ricci greater or equal to something implies the GH and the flat limits agree. So all the previous settings where you would kind of hope that all those previous results would just hold for intrinsic flat convergence. But now we have a setting where there is no Gromov-Hausdorff, so you need to get things to work using a new method, okay? All right, so we have just... So what we'd like with this generalized scalar, we'd like it to at least have that volume bound. We'd like it to at least say, we hope at least, that the limit as r goes to 0 of the volume of B0R in Euclidean space minus the volume in M, infinity, B0R divided by volume in Euclidean space, B0R, ought to be non-negative for the generalized scalar, for the limit space. I hope at least that much. Whatever kind of volume you use, So what kind of volume might we use? We could use Hausdorff measure. You'd hope at least that much.
Sorry, so what is the conjecture? I mean, there's a question. Do you conjecture an answer, or?
Oh, I'm sorry. He conjectures yes.
Okay.
Then a subsequence converges to M. Intrinsic flat converges to M infinity with scalar greater than 0. What? Period. But what is that? That's the vague part. What is the scalar non-negative part? Okay. Now we already know an intrinsic flat converges to an M infinity from Wegener's compactness theorem. The hard part is how do we check if the limit actually has some non-negative scalar? So you would like it to have this property. So this is where the paper with Joseph and Jorge comes in. So examples which disobey this conjecture. We're going to start with spheres again. So we're going to start with three-dimensional spheres. Oh, this purple's no good. Okay. I'll draw 3 pictures before we get to our limit space here. Now we have a number of them. I'm going to draw the most basic example because it's kind of neat. Take a geodesic that just goes around the equator. So this is a gamma. I'm just going to put in all of them. Gamma, the geodesic. And S3. And now what we're going to do is we're going to start sewing. What is sewing? The name of the paper is sewing. Okay. So what we do is we're going to put in, this is Jorge's best part. He decided to stitch it this way, which is to make the stitches kind of using a sewing technique like this, which is one of the standard methods of sewing, where you space it in pairs, your stitches. So you go stitch, 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 that kind of a pattern. So you have this pattern here. And then we're going to stitch smaller. Right now we're just choosing balls. So tiny pairs. I should do that much closer. Anyway. I'm not going to build those balls, I'm going to build dashes. Okay, and then, okay, now what are we going to do with each of these things? How are we going to actually sew them? So we're going to look closely at this, and I'm going to take this big jump, 1 to 1, and then 2 to 2, and then 3 to 3, okay? The ones that are far apart are labeled together. And now I'm going to blow up the picture so we can see it. There's our S3, right? And here's another copy of the S3. And here is the first ball in S3. This is the 1, let's call it 1A, and this is 1B. So 1A and 1B. 2 ends of a tunnel. We're going to make a tunnel between them. Now this is the exact same S3, but I'm looking at it from a different perspective. So this is the piece of 1A and the piece of 1B. I'm sewing them together. So I'm thinking of the piece. This is the same sphere, but I'm taking those 2 parts close and I'm sewing them together with a tunnel, like that. And now I've cut it, and I've made this super short tunnel here. This is called a Gromov-Lawson tunnel. And to cover your bases, Schoen-Yau. Okay. All right, so this is scalar greater than 0. And they had already observed that if you have a sphere and you have another sphere, you can make a tunnel between them. And you can make this tunnel like this, and it'll have positive scalar afterwards. What they didn't do was say how big the tunnel was. Okay, they drew this picture like this, but they didn't say the tunnel's huge or long or anything. So then, in the appendix to our paper, which is really the work of just these two guys, because I don't have patience for this, they showed that the tunnel is tiny. Can make the tunnel arbitrarily small, short, and small. This length is small, this radius is small. Both of them, as small as you wish. Fixing this curvature here. That's why we can do the sewing smaller and smaller and tinier and tinier.
And it's not two separate copies of S?
No, I'm taking two pieces, it's like a cloth.
And you just...
I'm taking my two pieces of cloth and I'm sewing them together.
Okay, yeah, that's right. I was trying to make sure that, okay.
So here's when I'm doing my work and I'm sewing them.
Yeah, right, okay.
Okay, so this is a Stargate. If any of you have seen, this is really seriously what a Stargate is, or in Contact, when they go inside the sphere and she pops out somewhere else. This is really what this is. This is an old notion. That the idea that you can go from one part of space and then jump to another part of space going through a tunnel. That's what these things are. But like you'll notice in all those movies, they go through a tunnel for a while. Okay, but no, you don't have to. The tunnel is super short, okay? All right, so we can make these tunnels really tiny. I can do them right here. You won't even know they're there. Yes, you will. Actually, you will know they're there, because what happens is, if you live over here in our universe, and your friend lives over here, and you want to go visit each other, you're going to jump down to your nearest tunnel. Hop, go outside, jump into the next tunnel, hop through the tunnel, go outside, go to the next tunnel, hop through, come out, and go to Q. So P and Q are really not that far apart, and they can keep up their friendship. No problem. And, well, wait a second, P has an even closer tunnel in this version and can get out to Q. And we're jumping over. This sewing trick means you're jumping over much more than you're traveling out. That's why the pairing is so good.
So in the picture, 1A and 1B are not close together in the original?
1A and 1B are not close. They're along the route. This is the 85th Street stop, that's the 96th Street stop, okay? All right, we're just jumping. But you have to jump out and switch trains every time. Okay, we have to, because it's really a series of tunnels. Okay, so you do the series of tunnels, we call this sewing, and the limit space you get from P, who's in back of the sphere, to Q, the actual distance is exactly just this distance of the green line. The distance from P to Q is S1 plus S2. S1, S2. Exactly. This is what's called a pulled string space. And that term is from before us. A pulled string space. This is Barago's term. These are examples of not Alexandrov spaces. That's why they have these. So a pulled string space is, it's easier to picture two-dimensionally. Take a cloth sphere, so around the equator, hold a string. And that space that you have there, where the whole equator has been identified to a single point, that's a pulled string space. Okay? We did it in 3 dimensions because we are trying to keep scalar positive. To keep scalar positive, we need 2 directions of positive sectional here to make up for this negative. So that's why we start in dimension 3. Joseph is doing higher dimensions, or has already done them. Basically, has already done them. But you can't do it in 2. I mean, you can sew in 2, but it won't have positive scale. Okay, it's got negative. Okay, so we've got this picture. This is a pulled string space. And this limit space, we can call it X. Actually, we can call it S3 modulo equivalence, where all the points X and Y on the green, gamma T is equivalent to gamma T2 for all T1 and T2. So all the points on that geodesic are identified to a point. Okay. So this space fails. This space fails this hypothesis, this notion of generalized scalar. Okay, and the reason is that if we take the ball P that we're talking about and we make it this green geodesic, the volume around that green geodesic, the Hausdorff measure, you can actually compute it. Okay, you compute the Hausdorff measure of the volume of a ball around this green geodesic. So the volume, let's call this space X, in X of BPR, where P is our collapse, our zone point, or pulled point, is equal to the volume in S3 of the tubular neighborhood of radius R around the gamma. And that's failing. This is way too large a volume. It makes this limit go to negative infinity. So star equals negative infinity. All right. Okay. So now what do you do? Well, first you might say, well, let's check if at least some other kinds of notions of non-negative scalar work. Maybe this one isn't a good one. So there's two other ones, and in further work in his thesis, there are two more examples, which I'm not going to describe here, but they basically show other properties of non-negative scalar also fail. So there's also some examples showing that the positive mass theorem will fail, which is a theorem that has to hold for non-negative scalar. And there's an example that shows that the torus rigidity theorem will fail on these limit spaces if we allow these kinds of zone limits. So in our paper, we changed this deliberately vague conjecture, and now we add one more condition. Instead of, so that we can hope to have all the proper answers. And so the new conjecture is, and min A of MJ is bounded below by something greater than 0. And I want to explain that condition rather than all the other examples. Okay? So that condition is saying, and then we do hope to have this. Okay? This is our fix. Extra hypothesis. Gromov conjecture. So I want to explain that extra hypothesis. And then there's various people in this room actually working on studying that situation and this theorem. So let me just write down the Min-A hypothesis. And I'll explain why it's natural, and then that'll be the end. So min A of a manifold, and this is a three-dimensional. I'm going to make it three-dimensional because this hypothesis is a three-dimensional version, is equal to the infimum of the area of a closed minimal surface. M3. So we're adding the condition that the smallest area of a closed minimal surface is bounded below uniformly. What this condition does is it prevents tiny sewing, because right here is a closed minimal surface. Okay? Right here, like Lawson's name. This is a closed minimal surface. It's stable. Closed minimal surface right there. And when we're sewing, we're making more and more tiny ones like this. So we've just prevented sewing. So this ends all our sewing examples. But you might say, it's just fixing one problem. Okay? But why should areas of minimal surfaces be anything to do with scalar? Well, Schoen and Yau have a whole lot of theorems about minimal surfaces with non-negative scalar, and Brendel and Neves and Marquez. So we've got a whole world of results about minimal surfaces in 3 manifolds with non-negative scalar. And they really do say things like what their areas are, and rigidity theorems about them. So I could give a whole another hour talk about all the things about these guys. So this is something that is controlled. The minimal surfaces in 3-dimensional manifolds with non-negative scalar are the kinds of things that can counterbalance. And this would also prevent collapsing, which was another possible problem that could have happened, which is that your spheres could just get very thin, sort of disappear. But it doesn't stop all those. The Illmann example satisfies this. There's no, the minimal surface in the Illmann example are big. They go around the sphere. There's no minimal surfaces caught on those wells. And the other thing you should keep in mind is that minimal surfaces, they're called the horizons in general relativity. They're the black hole horizons. So in general relativity, the general attitude is, we don't care what happens on the other side, just cut them off. So we should just change this to mg has volume like this, allow it to have boundary, cut the minimal surfaces, and hope that this is still true. Just add area boundary mj, also less than or equal to some constant. So we can still use Wenger's compactness theorem for that case. And this just means we're going to cut. Then you can cut anything like this. So if we cut this guy at all the minimal surfaces, we just cut all the threads, and now it doesn't get a pulled string anymore. So if we cut all the threads here, this actually converges to a sphere. It's like cutting every thread. So
The minimal surface stuff is only in dimension 3, really?
this conjecture is purely dimension 3 conjecture because I am not touching the higher dimensional. Joseph has done some of the sewing in the higher dimensions, but it's not clear. Your surfaces and then hypersurfaces, minimal hypersurfaces, right? You did the sewing in one codimension. Yeah, it's still hypersurfaces. But the problem is you can't just say just removing them stops some sort of lower dimensional sewing.
Yeah, right.
So I'm not going to touch that.
No, it's fine. No, that's fine.
Right. So yes, we can do sewing with hypersurfaces appearing, but we can't be sure that maybe there's something lower dimensional that could be also going on. You have to keep track of that.
Yeah.
So let's just stick to dimension 3, and also a lot of the results are 3-dimensional.
Yeah.
About these
Yeah, no,
guys.
it's fine.
Yeah. Okay, so that's basically the talk. Thank you very much.
Very silly question I may not have heard. Is this a theorem already, the case dimension 3?
Conjecture.
Conjecture, just checking.
It's a fix of a conjecture, but thank you for clarifying that. A little less vague and more true, but not all the way true. Yes.
So suppose collapsing happens instead of the string phenomenon happens. That inequality is not.
This will prevent the collapsing.
Yeah, but let's suppose before imposing that condition.
Yeah.
And suppose collapsing is one of the bad situations.
Yeah, he didn't care about that because the limit was empty. So if it's empty, he didn't that had non-negative scalar because it's empty.
Yeah, but then also the non-negative scalar condition is not violated actually.
That's
Okay,
right. If it's completely gone, this is not valid. That's why he didn't mind making his conjecture. If it's disappeared, this is true for every point in the space.
But
what's nice is that actually this will prevent the collapsing too. So we'll always, I conjecture that this prevents the collapsing, and so your M infinity will actually always have points as well.
So do you think there should be some other notion that allows possible collapsing to happen?
Intrinsic flat doesn't give us any information with collapsing. There's no geometric measure theory notions that handle limits that handle collapsing. Yeah, so that would have to be dealt with completely new techniques.
And another question is, so all in this talk is scalar non-negative.
Yeah.
Is the scalar uniformly bounded below a similar situation?
Same story. But again, sorry. Scalar non-negative goes very well with minimal surface. Scalar bounded below doesn't have all those Schoen-Yau theorems.
non-negative scalar, then if you have a Stableman surface, it satisfies some nice things. For example, it has to be a sphere by Schoen and Yau. Okay, so I wouldn't say scalar greater than negative constant, but scalar greater equal to something positive. Sure, you could look at that.
And also in the Alexandrov space theorem, so the Alexandrov, the Alexandrov
Yeah.
non-negative implies the Gromov-Hausdorff equals the intrinsic flat convergence.
That's
That theorem is valid for any lower bound, Scalar Curvature lower bound.
that's
Actually Alexandrov lower bound.
I don't recall. It should be. I imagine it could easily be proven because in that case there isn't a big difference. It's triangle inequalities. But the problem is that, so in paralysis proof, I'm pretty sure she does non-negative, and that's partly because then you don't have to worry about scaling out to use some things that Branko, Gromov, and Perelman prove that there are things called strainers, which are especially nice charts, and she uses those.
Let's thank the speaker.